So let's apply the same principle and try to guess a power series solution in this higher dimensional context now. So A will be an n by n matrix, so maybe 2 by 2 like the examples we were looking at before. And X will be a column vector with n functions. So this is like our n dynamical variables that describe the state of our system. All right. So we're going to guess functions that can be written as power series. So let's see how we can do this. Let me start without paying any mind to efficiency. So x of t to begin with is x1 of t, x2 of t, etc. down to xn of t, right? Let's call them that. Usually I say x of t, y of t here, or x of t, y of t, z of t. But if I want to allow there to be n of them, with any number of them, then maybe this is a better naming system, right? Then my guess for power series is that each of them is a power series. So x1 is like C0, 1 plus C0 C1. Let me index these well. C1 1t plus C1 C2 1t squared, etc. And then similarly here, C0 2 plus C1 2t plus C2 2t squared, etc. So you see what I'm doing? There's a family of coefficients for each one of these. So here there's a family of coefficients that are all called C0 something. And here there's a family of coefficients there, that are all called C1 something. So these are the C0s, the C1s, and we're going to continue. So here we have C0n plus C1 nt plus C2 nt squared plus, and so on. I don't know why I didn't give myself room here. So each of these we're assuming is this infinite sum. And there is definitely a better way to write this. So if I think of the C0 somethings, C01, C02, etc., as a vector of C0s, then I could, portion this entire thing off. How about I do it this way? Let me do this more step by step. So here's my guess, trying to write it out a little bit more efficiently. So I've got my C0 somethings, C01 up through C0n. And then here I've got my C1 somethings, C11 up through C1n, all times t, right? So here I've got, sorry, I don't know why my plus sign looks so weird. Okay, all times t. So this is like a vector times a scalar. And then my C2 something, C21 down to C2n, all times t squared, vector times a scalar, etc. And then I could call this all C0 vector, which is like a package that contains all of these. C1 vector t. Now this looks a little bit weird. Usually we write the scalar and then the vector, right? TC1 is more natural to write. It doesn't have to be that way. I just personally I like writing scalar and then vector. That feels more right to me. And then t squared C2 and so on. So this is our guess. So let me write this in kind of a more compact way here and just write our guess like this. So there's our guess. Now let's plug in the guess. So I need to know the derivative and take the derivative of this, plug it into the left side, and then apply a to this and put that on the right side, and then set them equal. So for the derivative, if it's a wonderful convergent power series, then we have this property that we're just going to get C1 the derivative of this constant will be 0 across the board. Then here we'll get C1, here we'll get 2t C2, and so on. And then on the right side there, AX, that will be A C0. The A just distributes. And you can pull the T out if you want. So A C1, A C2, and so on. Now equate these and equate coefficients just like we did in the last video. So at each level, so this is like n equations when you equate these. So finally, to plug our guess into the differential equation, I need to set this equal to this, right? So then let me erase these and then make this a big curvy equal sign. So I need to set these equal. This equal to this. And then just like last time, in the previous video, we're using the fact that the functions, t squared, 1, t to the 0, t cubed, etc. These are linearly independent functions. So if you want this to equal this for all values of t, for all real numbers t, then coefficients have to match up. And that has to happen for at all n components. So these are vectors here, and this is a vector equality. There are n components. That equality that I just described has to work out for all n components. So then you end up getting all n of the equalities, C1 equals AC0, and then all n of the equalities, 2C2 equals AC1, and then 3C3 equals AC2, and so on. And do you see what we're getting? Let me go back to our work from before. We're basically getting the same recursion rule that we had before, right? Except the C's now have a little vector symbol on them. That's all, right? And the A is now a matrix. So this is the same recursion rule we got before. And the A is now a matrix being applied to the appropriate C. So the result is that C1 is A C0, C2 is 1/2 A squared C0, but A squared here means A times A, so that's a matrix multiplied by itself. C3 is C3 is 1 over 3 factorial A cubed, so that's A times A times A, C0, and so on. C4 is 1 over 4 factorial A multiplied by itself 4 times, and then C0. Cn is 1 over n factorial, and then the nth power of A, this is a matrix power, so you have to multiply a matrix n times by itself, times C0. All right, so we have found, after plugging in our guess, that x of t equals, and then here's the vector in front of t to the power 0. It's just C0. That one is allowed to be anything. And then tc1, that one should be, what was the rule? C1 is A C0, right? So here I have t A C0. And then t squared, my face is covering the index, t squared C2. There we had 1/2 A squared C0. So that half is actually 2 factorial. Then 1 over 3 factorial t cubed A cubed C0. And so on and so on. It's an infinite sum. Now you see there's a common C0 here. So let me pull out the C0. But it does not work to, let me show you what we did last time. Back here where we had numbers and A was a 1-by-1 matrix, so it was just a number. I could take the C0 and I could just pull it out and write it down on the left side, right? That's because A was just a number being multiplied by C0. But here, C0 is a column vector, and A is a matrix that's getting applied to that column vector. So the matrix has to be on the left and the column vector on the right. Otherwise, it changes the meaning of what you're looking at. So if I pull out the common factor of C0, then I'm forced to put it on the right side. So there's a common factor of C0 here, and then what's getting applied to it is a bunch of stuff in an infinite series. So this first term is the identity matrix applied to the vector C0, right? And then over here we have T times the matrix A getting applied to the vector C0. But you see how this has to be to the left of that if I want to get this term. And then there I've got 1 over 2 factorial T squared, A squared getting applied to C0. 1 over 3 factorial T cubed, A cubed getting applied to C0, and so on. There's an infinite series of terms here. And then, just like last time, we take this as our definition of the exponential of a matrix, at least when you plug in t equals 1, just to make things easier. So this at t equals 1 shall be called the exponential of A, of the matrix A, the exponential of a matrix. And often we write this as e to the A, even though A is not a number. It's sort of weird to say, like, usually when someone writes 3 to the 5, right, they mean take the number 3 and multiply it by itself 5 times. If someone says e to the 5, they're saying take the number e and multiply it by itself 5 times. Well, what if A is a matrix, if it's like the matrix 1, 2, 3, 4? What does it mean to multiply e by itself that matrix number of times? Well, that's not very meaningful. Instead, we take this notation to just mean what we're calling the exponential of A, which is this power series. So let me just write the definition clearly once here. The exponential of A, also written as e to the A, a little bit strangely, is this series where I'm plugging in t equals 1 here. That's the exponential of a matrix. Just like the exponential of a number, if A were a 1 by 1 matrix, then this would literally be the magic number e taken to the power of that number. But now we're allowing A to be a matrix. And I hope you're seeing why this is useful. It's giving us a solution to that differential equation. Let's be clear about exactly what the solution is here. So this is our solution. It's e to the, and then what's this? So this thing in brackets here is e to the ta, right? It's like this, but with ta in place of a. You can see that if you write, instead of t squared a squared here, and instead of t cubed a cubed here, write it as ta squared, ta cubed. Those really are the same thing. Often you worry about this kind of thing when you're working with matrices, but like ta squared is ta, right? And you can reorder this matrix times a scalar and write it like this. Normally you would have to worry if you were multiplying two matrices together and then trying to look at the square of that versus the individual squares. It might actually not be the same. But if it's a scalar in a matrix, you can totally pull the squaring out like that. Yeah, so here we have e to the ta apply to C0, right? So let's think about all the different types of things that we have here. So e to the, okay, so C0, that's a vector, right? That's what we were calling C01, C02, C03, etc. It's a column vector with n entries. So let me keep that information there. So this is, let's call it an n vector, a vector with n entries. Column vector with n entries. And then what's this? Well, it's whatever the heck this is here. What is it? It's an infinite series of matrices, right? This is a matrix, this is a matrix, matrix, and then we're adding them up in an infinite series. The result should be a matrix, assuming the series converges. It turns out it always does. This one always does. So this, the exponential of a matrix is another matrix. So this is an n by n matrix. So we're taking an n by n matrix and applying it to a column vector with n entries. The output should be a column vector with also n entries. That's the kind of thing x should be. So at least the types of things check out here. That's good. Okay, so here's what we have achieved. Given the differential equation x prime equals ax, you can immediately write down the solution. Solution is x of t, the general solution is this. And then you have this n free parameters here contained in this vector, right? And actually, one neat thing about this is look at what is e to the, so what's x of 0? If I plug in t equals 0, that would be e to the, and then 0a, that's the 0 matrix. So this is 0 matrix. I don't know how to express that I'm talking about the 0 matrix. How about this? E to the 0 matrix, C0. What's e to the 0 matrix? So let's think about that. If I put in the 0 matrix for A, then all of these terms here vanish except for this first one, which is the identity. So e to the 0 matrix is actually the identity matrix. So we get identity matrix applied to C0. And that's just C0. So the initial condition is x of 0 equals C0. That's really awesome, right? Like normally, when you write down your general solution and have a bunch of free parameters, the free parameters are related in a possibly complicated way to what you want to be your initial condition. So given an initial condition, you have to solve a bunch of algebraic equations in order to figure out what the parameters have to be to satisfy your initial condition. But here, given an initial condition, as long as it's at time 0, that initial condition will directly just be that vector of parameters. So what I'm saying here is, given x prime equals ax, this is the solution that satisfies the initial condition x of 0 equals this vector of initial condition, C0. So that's the role that C0 is playing here. It's your vector of initial conditions. So that's very cool. Given differential equation with a matrix of coefficients and given initial condition, so given like an initial value problem, x prime equals ax, x of 0 equals, let's call it x naught, a vector of initial conditions. So given this initial value problem, here is a quick way to write down the solution. First, figure out this matrix e to the at. Okay, that might take a while, but maybe we can do it. We're actually going to talk about it pretty soon. So work out what this power series is. I would not recommend directly trying to compute the power series, but you'll see there are ways to do it. So somehow work out what this power series is. Then your solution will be that power series applied to the initial condition. So this will be a matrix, now just apply it to the initial condition. And the effect of applying this matrix to your initial condition is to flow along solution trajectories in the phase space by time t, starting from here. So this is a matrix that when you apply it to a vector, it sort of, when you apply this matrix to initial condition vectors, it flows them along by time t along solution trajectories in phase space. So this will be your solution. It's a very cool setup, as long as you can compute this. So next question, how compute? What do we do to actually compute this in practice?